Far, we have explored properties of sets and also introduced Venn diagrams as a way to visualize operations and potential properties. We're now going to move to arguments and counterexamples as the way to rigorously prove a property, not just visually support our intuition that the property holds. We're going to start with the concept of a subset. So recall, what does it mean to be a subset? If I have a set T, that's going to be my bigger set. S is a subset of it if it, on the Venn diagram, lies fully inside of T. So there's S right there. That means, in fact, according to the definition of what it means to be a subset, it means that for every element X in S, it also belongs to T. And that is how proof of a subset property will work. We're going to pick some general representative X of a set S, and we're going to prove that if it lies within S, it then also implies that it lies within T, which means that S must be a subset of T. If we are to prove that something is not a subset, we're going to have to show that there's an element that does not actually obey this property. So in terms of sets S and T, what that actually means is if I have a set T, if S is not a subset of T, so S doesn't fully lie within T, that means that there's some part of S that doesn't belong to T, which also means then, of course, that there is an element X out here that belongs to S but does not belong to T. This X is going to be our counterexample. Apologies, watch the typo here. So, if we are to prove that S is not a subset of T, we will need to find such an X that, while belonging to S, does not belong to T. Let's do a concrete example of this proof to see how this works. I'm going to consider two sets, A and B here. A is a set of integers of the form 6a plus 4 for some integer A. And B is a set of integers of the form 3b plus 1 for some integers B. Now, it might be difficult to capture what exactly those sets are, so it is a good idea to write out a few of the elements so that we can get a grasp on what format those elements within each of these sets actually has. So if we write out the few elements of the set A, what are we going to have? Plug in some numbers for A. So A has to be an integer. Let's plug in, for example, minus 1. If I plug in minus 1, I'm going to get minus 6 plus 4, so negative 2. If I plug in a 0, I'm going to get 4. If I plug in a 1, I'm going to get 10, 16, and so on. So these are some of the elements of my set A. I'm going to go through a similar procedure to get a grip on some of the elements of a set B. So notice that I'm putting dots in front and dots at the end because I know that what I'm listing is just some sort of middle chunk. If I plug in, let's say, negative 1 for B, minus 3 plus 1 is minus 2. If I plug in 0, I'm going to get a 1. If I plug in a 2, I'm going to get 4. I'm going to get 7, 10, 13, 16, and it keeps going. So, simply by inspecting what I get, I notice that in my very short list of the elements that I've explicitly found, some of them actually do match. In fact, in what I have, it appears that every element of A lies within B, but not the other way around. So my conjecture is that A is a subset of B, but B is not a subset of A. Now, the trick, of course, here is I can't just state that. I will have to somehow justify it. So first, let me write out what this claim actually means sort of in English. It means that every element of A is also element of B. And if I am to prove that B is not a subset of A, that of course means that there is some element of B that is not in A. Now, in both of these cases, the way we're going to go about the proof is going to be different because the statements are very different qualitatively. The first one says every element of A is also element of B. Well, A is an infinite set. There's no way I can check every single element because I don't have infinite time or patience to go through all of the elements here. So that means that I'm going to have to find some generalized argument to use here. On the other hand, this one says there is some element, not every element, there is some. So all I need to do is find one element for which this property holds, and I am done. If I'm proving something universally for every element, I'm going to have to prove it. If I'm after some element, a counterexample, then all I need is one. Okay, so let's see how this works here. Every element of A is also an element of B. So, as in fact, per my structure here, I'm going to start with the set that is the alleged subset. So I'm going to start with A, and I'm going to pick some generic representative of a set A. Let's call it X. So I'm going to suppose that X is an A, and I'm hoping that through some logical steps, I'm going to arrive at the conclusion that X is then also in B. So I know my first step in my proof, I know the last step. All I need to do is find this middle. And of course, I'm going to use the structure of my two sets in order to fill in these middle steps. So if X is an A, what do I know about X? Well, in A, all of the elements are of this form. So I know that X is of the form 6A plus 4 for some integer A. Now, if I am, again, keeping my eyes on the ball here, if I am to prove that X is also in B, I need to write X in this format, which is what all of the integers in B look like. So, can I somehow manipulate this expression into being 3 times something plus 1? Well, 6 is 3 times 2, so this 3, I can at least see where I can get it from, but 4 and 1, maybe let's split it up. So first I'm going to say it's going to be 6A plus 3 plus 1. Okay, I haven't changed the expression. 4 is indeed 3 plus 1. I'm pretty confident in that. And that what I'm going to do next is I'm actually going to take these two terms together and factor out a 3. Okay, so I'm going to take 3 out. What am I going to get? So taking 3 out from 6A, I'm going to get 2A. Taking 3 out of 3, I'm going to have 1 left. And then this plus 1 on the outside, I am still keeping with me. Well, this is looking much better actually, because look, I can simply take this bracket and I'm going to call it B. I'm simply going to relabel it because B in the definition of the set B is just some integer. If A is an integer, multiplying it by 2 and adding 1 will keep B as the integer as well. Now, I've simply relabeled the things, so I can just rewrite this as 3B plus 1, where B is actually going to be 2A plus 1. Now, of course, this is exactly the form of the elements in B, which means that my ultimate conclusion is that X is actually an element of B. So let's review what we actually have now. We started with supposing that X belongs to A, and through a series of logical steps, we have shown that that implies that X belongs to B. Now notice that there was nothing special about choosing this X. This was a generic representative, not something in particular. We've assumed that it is of the general form that every single element in A is in. So that means that this argument actually holds for every element X in A, so taking any one of them will also mean that that element belongs to B. And therefore, we have actually finished proving our claim here. Okay, and we're done. People like putting little squares at the end of their mathematical proofs just to signify that this is in fact the last statement and the claim has been proven. Now, the other direction or the other non-direction, let's say, was we suspect strongly that B is not a subset of A because we spotted quite a few elements inside of B that do not belong to A. And remember that in order to prove something is not true, all we need is to find an example for which it doesn't hold. We cannot do it here because we're trying to prove something actually holds. So we can't find infinitely many justifications for that, and that's exactly how many we will need, because we need that it holds for all of the integers of which there are infinitely many of. But if we're trying to prove something does not hold, we only need to find some case when that fails. So pick your favorite element out of the ones that you're seeing that belongs to B but does not belong to A. Now, let's say I like number 7, so I can see that 7 belongs to B. It's not as easy, though, as just saying, well, clearly it does not belong to A, right? Sure, it doesn't go between 4 and 10, it doesn't appear there, but that doesn't guarantee that it doesn't appear somewhere else in the ... that I have been too lazy and economical to write out. So I need to rigorously prove, again, using the formats of the integers in A and B, that 7 never appears in this form, okay? So I'm going to take 7 belongs to B, and through the series of logical steps, I'm going to try to conclude that 7 does not belong to A. Now, if 7 is in fact in A, it would have to be of this format. So I'm going to make some kind of assumption that maybe 7 can be in A. Can 7 belong to A? If it does, what are we going to have? 7 belongs to A, which means that it can be written in this format. So 7 can be 6A plus 4. Now remember that the format assumes that this little a actually has to be an integer. So let's see what this equation implies for this a. If I just move things around here, what am I going to get? This is equivalent to 6a equals to 3, which is equivalent to a being 1/2. Is 1/2 an integer? No, 1/2 is not an integer. But now what we have is, if 7 was an a, it would have to be writable in this form, but that seems to imply that a, for which that form would be feasible, is not an integer, which then implies that there is no possible way that 7 can be written in that form, and therefore 7 cannot be an element of A. So let's review this part. We started by assuming that 7 belongs to B, and through a series of steps, we have shown that it does not belong in A. So we found an element in B outside of A, which means that B cannot be a subset of A. Okay, and we are done with this part here. Excellent. So this is how element proofs work. The reason we call them element proofs is because we are working with assuming something is an element of a set and show that it either implies it's an element of some other set or it implies that it is not an element of another set. But the entire focus is on proving something about elements belonging to sets. Once we have done the proofs that something is a subset of something else, we can move on to the idea of equality of sets. And in a sense, this is similar to the biconditional. A is equal to B if and only if A is a subset of B and B is a subset of A. So both directions have to hold. And if you are to prove something is equal to some other thing, you will actually have to go through both directions of the proof. So here we have an example with two different sets A and B, not the exact same ones as above, and we're asked to prove that A equals to B. In fact, just to review this very quickly, this is one direction, but the second direction failed, which means that in this example here, we can automatically assume that A is not equal to B, because we have indeed shown that one of the subset inclusions does not hold. If they both hold, then we have proven the set equality. So in order for us to prove that A is equal to B here, we're going to actually go through two different proofs. The fact that A is a subset of B and the fact that B is a subset of A. So yes, this is going to be sort of, it almost feels repetitive because both of those proofs are going to have very similar feels in both of them, but we will have to go through both of them for the sake of completeness. I'm going to do this one because it's a little bit more complicated, and I'm going to leave this for you to finish off. So A is a subset of B means that I'm going to suppose that X is an A, and I'm going to then show that that implies that X is also an element of B. And just for the sake of stating what we're going to need to actually do, I'm going to rewrite this exact statement here, except for I'm going to have to swap the roles of A and B. So in this case, I'm going to have to assume that X belongs to B, and I'm going to then show, so there's a bunch of steps in the middle here, that implies that X belongs to A. So back to this example, I'm going to assume that X is an element of A. X is an element of A implies what about A? Well, everything in the set A is of this form, 2 times little a, where A is an integer. So if X is an element of A, it means that it can be written in the form 2 times little a for some integer A. And this is already, remember, key. A actually has to be an integer because something not being an integer last time is exactly what ruined our proof. Now, if I am to show that X belongs to B, I'm going to try to write it in this form. So 2 times something plus 2. Well, I have the 2 times something here, but I don't have the plus 2. So I'm going to have to think about where I can get that from. And a trick that I can apply here is, well, if I would like to have a plus 2, I can subtract 2 and add 2. Right? This is the part that I really want, but in order for me to keep writing equals, I'm going to subtract and add 2. I haven't done anything, but I have acquired an element that I was looking for. Now, the next thing to think about is, well, I don't need, I can't have quite this yet. I have the plus 2, so now this is good news. But my other portion has to be 2 times one coherent thing, whereas now I have a difference. But here, I can do something similar from what we've done above and just factor 2 out. Okay, be careful about factoring. If you're factoring 2 out, this is not just going to go away. You will actually have 1 as a factor left over. Now, if A is an integer, then A minus 1 is also an integer, and this is what I'm going to call B. So I can confidently claim that if A is an integer, B is also an integer, and therefore this is actually of the form 2 times B plus 2, which is an integer, and is of the format that every element is in the set X. So this immediately implies that X belongs to B. We started off by assuming X is an A, and through a series of logical statements, proved that that implies that X belongs to B. Therefore, A is a subset of B. I'm going to leave this for you to fill out. So once again, we're going to start with assuming that X is in B and go through the steps and hopefully reach the conclusion that X is an A, which will then prove that B is a subset of A. If I have A is a subset of B and B is a subset of A, together, these two parts will imply that A is in fact equal to B, and we're done with this exercise. Let's review here. What we have just proven are specific properties for specific sets. We used element arguments in these cases to prove something is or is not a subset of it, and extended this to proving that two sets are equal. Now, in a similar way, we can actually apply element arguments to prove more general properties of sets overall. And that will allow us to produce laws that we can then use directly. Notice that a lot of these laws here have analogs from logic. And remember that in order to establish these logic laws, we first had to actually show that they hold using truth tables. In a similar way, some of these laws will be proven using element arguments, everything from first principles. Before we can get to that, though, let's just see what kinds of laws we can maybe establish as a base kind of thing, and see if we remember some of their analogs in logic. So we have here things like idempotent laws. These will have slightly different names, and that is just a notation within the book. It doesn't really matter. Some laws are sometimes called different things in literature. Idempotent laws tell you something about the fact that if you take a union of the set with itself, you just get the set itself back. Same with the actual intersection. Identities laws have direct analogs in logic in terms of, let's say, or applying an or to a proposition together with the contradiction, or applying an and to the proposition together with the tautology. Inverse laws, domination laws, commutative laws, of course, look very familiar. It doesn't matter whether you say A union B or B union A. Similarly, it doesn't matter if you say P or Q versus Q or P. Double complement laws. So here I've been using the notation C. Associativity laws mean that it doesn't really matter where to put brackets as long as the operation is consistent throughout, whereas distributive law allows you to open up these brackets if the operations are different. Finally, the De Morgan laws, which we have already had some evidence for throughout this unit, and so on. In order to be able to prove these, we also have to be able to go between the set notation or the set operations and the or the and operators on logic. So recall that these come directly from the definition of the actual set operations. The element x belonging to the union of A and B means that x is either in A or in B. So this allows us to go from the union to the disjunction. X is the element of the intersection if X is both in A and in B. So this allows us to go from the intersection to the conjunction. And then finally, X being an element of the complement is equivalent to saying that X is not the element of A itself. Now let's see how we can use our element arguments to prove some of these laws. And we're going to begin by proving one of the De Morgan's laws. So what we have is we would like to prove that the complement of the union is the intersection of the complements. Remember that proving set equality means that we need to prove the subset property in each of the two directions. So first of all, we're going to prove that the left-hand side is actually a subset of the right-hand side. And secondly, we're going to prove it the other way around. So the fact that the right-hand side is a subset of the left-hand side. So what we've seen on the previous page about showing both directions when it comes to set equality is going to be true for all proofs regarding sets if we're going to be using the element arguments. So I am going to do this direction. Recall, how do we prove something is a subset of something else? We're going to assume that X belongs to the left-hand side, and through a series of steps, show that that implies it belongs to the right-hand side. So let's write down what it is that we would like. We were going to suppose that X belongs to A union B complement, and then we're going to show that that implies that X belongs to A complement intersect B complement. So if we're going to start off by assuming X belongs to the complement, let's just write this out one more time to be very precise. What does that imply? Remember, the basic tools from the previous page say that if X belongs to a complement of something, it means that X is not in that something. So this implies that X is not an element of A union B. Not being an element of means that it is very specifically outside of that set. So we can say that it is false that X is in the union of A and B. So now we can expand this out using the definition of the union. So it is false or not the case that X is in A or that X is in B. Now, this is key here because we can use logic laws at this point because we have actually transformed a statement about a union into a statement about logic, and that is something that we've already encountered before. So it is false that X is in A or X is in B, so we can apply this false or not operator onto all of the things that we are very specifically negating here, right? So it is false that this statement is the case. So what we can conclude from here is it implies that X is not in A. And remember that we have to flip everything. So disjunction becomes conjunction. So it is then not the case that X is in B. And now, having applied logic, we're going to go back to statements about sets. So X not belonging to A means that X belongs to the complement of A, and X not belonging to B means that X is in the complement of B. Really struggling with positioning here for some reason. Okay. So what do we have now? This is looking promising. And again, as per the basic tools that I've just listed on the previous page, and means it is in fact the intersection. So X is in the complement of A, intersection X is in the complement of B, means that X is in the intersection of the complements of A and B. And that is in fact the step that we wanted to show. So we're done with this direction here. This direction proves that A union B complement is a subset of A complement intersection B complement. In order to establish the equality of the sets, we also have to actually show the opposite direction. And we will proceed in a matter similar to the previous one. So we're going to suppose that X belongs to the right-hand side, and then we're going to show that that implies that X belongs to, if X belongs to the left-hand side, we're going to show that it implies that X belongs to the right-hand side. I'm not going to go through this proof because it is in fact going to be very similar. It's basically identical to the proof on the left here, except for it's going to move in the opposite direction. So yes, it will feel repetitive and almost redundant, but it is absolutely necessary because what we've established so far is all of these steps go in this forward direction. We now have to ensure that we can claim that they also go in the opposite direction as well, and this is what this proof is all about. So I trust that you can fill this out by yourself. Once you've reached the necessary conclusion, that would mean that the subset quality holds in both of the directions, which actually establishes the equality here. So now that we know that someone has gone through the meticulous job of proving all of the set identities in the table on the previous slide, we are going to try to use them to actually prove other set properties. So this is our first example here. I would like to show that A union B minus A is actually equal to A union B. Now the operation of difference has not been defined yet, so here is the actual definition of the difference. B minus A is equal to B intersection not A. Let's construct a Venn diagram just to see what kinds of intuition there is behind the definition of this particular operation. So I'm going to have my sets A and B in the most general position here. And the definition is the difference, B minus A, is B intersection not A. Not A is everything outside of A, and I'm going to intersect that with B, so everything inside the circle B. Because it's the intersection, I'm interested in the common parts of the two shadings, so the part that is double shaded, and it's not hard to see that it's going to be this part of set B. So that gives some idea of why the operation is called B minus A. I took the entirety of set A and I subtracted away parts that belong to A as well. What I'm left with is the part of set B that is only its own. All right, so now the way that we use set identities is we're going to start with one side of this alleged equality, and I'm going to throw some set identities at it, hopefully ending up with the right-hand side. So let's start off with A union B minus A. Now, the first thing I can do is, of course, go from the difference to the intersection definition, because intersection is surely something that I am going to be able to apply more set identities to. Remember, just like with logical equivalences, if we're going to use laws, we need to justify why we're able to write equals here by providing the name of the law or the reason for the simplification. So in this case, I'm going to say that this line is justified by definition of the operation B minus A. Next up, what am I able to do here? Well, this is going to be a little bit annoying because I don't have my table in front of me. So just like in the case of the logical equivalences, I strongly recommend having the table by your side so you can refer to it directly. What I have here is A union, some kind of intersection within the brackets. If I am going to open up the brackets, this is going to be an application of the distributive law, so one of these guys. And what I'm going to end up with is A union B. As I open the brackets, I'm going to go through the first set, intersection A union not A. And again, I need to justify why am I able to do this. This is going to be by distributive law. Next up, what is it that I have a hope of simplifying here? Where A union B is already as simple as that gets. So I'm hoping that A union not A is somehow going to be able to be simpler. And if we take a look here, A union not A appears right here in the inverse laws. Means that I can simplify this expression to be A union B intersection the universal set. And again, I need to include my justification. This is true by inverse laws, or inverse law, one of them. Okay, let me see what else I can actually simplify. Again, A union B is kind of as simple as it gets, but now I have the intersection with the universal set. Now, of course, the table is not going to have something this complicated. We have to look at the underlying structure of this expression. And the underlying structure is something intersection the universal set. This something can be anything. It's just a set. So is there something in this table of law of sets that talks about a set intersection with the universal set? And we should see it, in fact, right here in the identity laws. A set intersection with the universal set is just itself. It doesn't matter what this A is. If I intersect any set with the universal set, I'm going to get my set back. So my set in this case is A union B. So intersecting with the universal set is kind of like doing nothing, which is why it's called the identity law. It's kind of like saying plus zero. So again, if I am going to be able to write that down, I am going to have to justify what law I applied to produce this equality. And that is true by identity law as per the table. And I'm done. I have shown that my left-hand side is in fact equal to my right-hand side, so I have proven this identity. Notice that as opposed to the element proofs, I don't need to go left to right side and then right to left side, because at every step I am not writing implies, I am in fact writing equality, which of course means that the previous expression is equal to the following and the other way around. So I only need to proceed in one direction here, saving me, I guess, being a little bit more economical. Just like in the case of logical equivalences, though, you do have to be able to apply these laws in a little bit more generality than actually stated in the table. So look at the underlying structure and see what law corresponds to that in the table that you are able to apply. This takes practice, as anything in math or in life in general. So here's more of the exercises for you to do on your own. The first set of 3 asks you to use element arguments to practice with that technique, and the second set of 3 asks you to use set identities to get a little bit more practice with that. Notice in all of these there is the operation of the difference being used. So again, just use the definition that we've recently introduced in this example in order to actually simplify within the first step, and then the laws in the table to do the further simplifications. Now, empty set is a little bit different, because in order to prove that something is an empty set, we have to prove that it actually has no elements within it at all. The normal approach would then to be supposing that it does have elements and producing a self-contradictory statement. So let's see how this works both within the element proofs argument and also how it might work with using set identities. So this is one of the laws in the table. A intersection not A is the empty set. Let's prove it from the basic principles of arguments involving elements. So we're going to start on the left-hand side, and we're going to assume that X actually belongs to this set, A intersection not A. So X is here. What does that actually mean? So remember that the reduction for the intersection is the connectivity of the and. So that means that X is in the set A and X is in the set not A. Now this we can simplify further by saying that X being in the complement of A is equivalent to saying that X is not in A. And what do we have now? We have a statement that says X is in A, and at the same time, X is not in A. Well, clearly that cannot possibly be true. X can't be both in A and not in A, which means that we have, in fact, derived a contradiction, which means that we have to go all the way back to our original assumption and recognize that it must have been wrong. We have come up with the statement that makes no sense, which means that our assumption must have been senseless to begin with. Our assumption was that X is an element of this set. If that is to be meaningless, it means that there was no X to begin with for the choosing, so that implies that what we have is the empty set. A intersection not A is the empty set. Once again, given that we have now proven this particular statement, and let's say we have gone through the trouble of proving all of the other set laws that are in the table that involve the empty set, we can use them directly. So here I'm asked to prove some kind of large set equivalence to the empty set. I'm going to see how we can apply laws from the table on the previous page or 2 pages ago to do that. So in order to do that, I'm going to start with the left-hand side here and look at it closely to see if there's anything I can actually apply. Now, as before, I'm just going to plop this table on the page while I am going through this proof so I have something to refer to. Okay, looking at the shape of this, I can see that my operation throughout is intersection, so the same. And I can see that I have, for example, A in 2 different spots. So I can use the associativity law and the commutative law to move things around and change up the order of the brackets. So I can say, I can go from here to, for example, A intersection A, intersection B, intersection not B, by the virtue of using commutativity and associativity in one step. Now, of course, I can write it all out, but these are pretty straightforward operations, so I'm going to leave it as is. What comes next is I see that I have A and A, or A sort of intersection A, which appears right here in the idempotent laws. A union A and A intersection A is just A itself, so I can replace it here. So I'm going to have A intersection B intersection not B, and this was the equality that I was able to produce using idempotent laws. Now, next up is I sort of have a feeling that I can simplify B intersection not B. So where is there a thing that has a set intersection with not itself? And that is within the inverse laws right here. That will produce the empty set. So I can replace this entire bracket with an empty set. So overall I have A intersection the empty set, and this is due to the identity laws. And now, what do I have for A intersection the empty set? Is there anything in the table that allows me to simplify that? And in fact, there is this thing called domination law. A intersection the empty set is just the empty set itself. So here I have domination law. And I have come to the conclusion that my original set is equal to the empty set, which is the thing that I was trying to prove. Okay, so once again, if you are using set identities or anything from a table, you do have to justify every step with the law that you're applying, because that is the only thing that allows you to keep the equality going. As we have already seen, disproving a property is often easier than proving it. If you have to show something is true, and therefore it actually holds for every element in the set, for example, then you have to go through element proofs or set identities. But if you have to show that something is false, all you need to do is find one case when that does not actually work. So in this particular case, let's try to see what we're after. For all sets, we are going to disprove this fact. If A is not a subset of B and B is not a subset of C, then A is not a subset of C. Now, this is a conditional if-then statement, so let's recall the logic here. The true implying false, the case of a broken promise, is the only time that the conditional statement is actually false itself, which means that in order to disprove it, I have to find a case such that the premises are true, but the conclusion is false. Premises have to be true, and the conclusion has to be false. Now, this corresponds to the following statement. We're going to try to construct sets where the premises are as they are, so they actually hold, but the conclusion is false. So instead of showing that A cannot be a subset of C, we're going to have to find the case when it in fact is. We're going to start by drawing Venn diagrams and then maybe construct sets that with actual elements that correspond to our Venn diagram pictures. The first few times that you construct them, you might not break it right away. So you might have to fiddle with your diagrams a little bit until you get what you want. Okay, your first attempt might not be your last one. So let's see, what are the things that we have? I want A not a subset of B, B not subset of C, but I need to have for sure that A is a subset of C. So I'm actually going to start with drawing this case, A being a subset of C. Okay, so let's say I have my set C here, and A is going to be a subset of it. So here's my A. Now, what can I do with the other properties? I need that A is not a subset of B, which means that I'm going to need to have that B does not fully contain A, that there's some parts of it that B doesn't contain, and I also have to have that B is not a subset of C. So that means that my B cannot possibly all fully lie within C either. Okay, so again, the first thing you draw might not actually satisfy both properties, and they both have to be satisfied, and that's perfectly fine. But just thinking about this and trying a couple of things out, I can see that something like this in terms of my set B will work. Let's double make sure that everything that I want to hold actually holds as a property. A is not a subset of B. No, we can see that that's certainly the case. All of A does not lie inside all of B. I can also see that B is not a subset of C because all of B does not fully lie within C, but A is in fact a subset of C over here. So it seems that we have managed to construct a counterexample. Now, we could leave it as the Venn diagram, or we can come up with specific sets that actually correspond to this picture. So I can come up with sets, let's say, of integers where the integers are distributed in the Venn diagram like this. So for example, I can have that C has elements, I don't know, I can actually maybe like put them here. 1, 2, 3, 4, 5. I can have a 6 out there and a 7 over here and maybe an 8 over here just for fun. Okay, so if I have something like this, I satisfy my Venn diagram here. What are the elements of A? So my set A has elements 7 and 8. My set B has elements 8, 4, 5, and 6. 8, 4, 5, and 6. And my set C has elements 1, 2, 3, 7, 8, 4, 5. 1, 2, 3, 7, 8, 4, and 5. Now, if I have explicit sets, I can also check these properties using these sets as well. A is not a subset of B. That's very clearly the case. 7 and 8 are not both in B. B is not a subset of C. So not all of the elements here appear in C. And I can see that clearly. For example, 8 does not appear in C. But A is a subset of C. Both of the elements here can, in fact, be found here, so that property certainly holds. Okay? So for disproving something, I need to provide a particular case when the true premises are followed by a false conclusion. The other interesting, not quite a disproof, but a completely out of the left field statements are what we call paradoxes. We've already seen that before in the logic section, but let's review it here. This statement is false. Remember that if this is indeed a proposition, then it should have one of the two truth values. It's either true or it's false. If I suppose that this statement is true, then reading it, this statement is false, implies that this statement is in fact false. If I assume that this statement is false, that means that it is not the case that the statement is false, which implies that it is of course true, and I am stuck in a situation of a self-contradictory statement. If we assume it's true, then it actually implies that it's false, and if we assume it's false, it implies that it's true. So which one is it? It's neither. It's in fact not a proposition at all because it is self-contradictory. The example that involves sets is the following. The barber shaves all those and those only who do not shave themselves. Does the barber shave himself? So we can think of the sets of people here, the sets of people who shave themselves and the set of people who do not shave themselves. Which set does the barber belong to? Well, there are two cases. Either the barber belongs to the set of people that shave themselves. So let's start with that. Barber shaves himself. Well, are we going to have a problem with that? If the barber shaves himself, what does the statement say? The barber shaves those and those only who do not shave themselves. But he does shave himself. which means he can't possibly shave himself. Okay, well, that's a problem. What if we assume the other way around? Maybe that is going to work out. Barber does not shave himself. Is that going to produce some kind of an issue? Well, if he does not shave himself, then he's in fact in this case. And that is a set of all of those people who the barber actually does shave. So if he doesn't shave himself, then he does shave himself. So this is also a problem. Therefore, this is also a paradox, a self-contradictory statement. The solution to this problem, don't worry, we haven't broken math just yet, that there is in fact a solution. The solution to this problem is to make sure that when you define a set, so for example, people who shave or do not shave themselves, it must be a subset of a known universal set. So it must be well defined. And in fact, this is a big problem to which the sort of common conclusion is the fact that math cannot be free of contradictions. And this is a known result. In 1931, Gödel, a famous mathematician, showed that it is impossible to prove that math is free of contradictions. No matter what system you're in or what kinds of definitions you're working with, you will always be able to come up with these self-contradictory statements because math cannot be free of contradictions entirely. Again, as much as in life, it is in math that we will inevitably run into these types of contradictions, but as long as we have a well-defined system, we will be able to work around them.